that's going to be half Li naught square. That's the total heat dissipated. Half Li naught square, right? So this is what the problem seeks. This is the solenoid participation in Joule heating. This is what it is. Clear? So now this L1 and L2 could be replaced by 1L, which is L1 L2 by L1 plus L2. What we need to find is, in this case, the current as a function of time through L1 and current as a function of time through L2. So in any case, I do know I as a function of time, total current I as a function of time, because this, and there must be a resistance capital R somewhere, yeah. This is the same as L, which is L1 L2 by L1 plus L2. The current I as a function of time then would be, I would be E by R into 1 minus e to power minus t into R by L. That's how current passes through a battery as a function of time. This L1 and L2 replaced by one single L equivalent, right? Now, out of this current I1 will pass through L1 and I2 will pass through L2, right? And it will be such that the drop across this is the same as drop across this is the same as the drop across the equivalent, isn't it? Huh? So then L1 di1 dt is L2 di2 dt is the same as L di dt, is the same as L di dt. That's why that's the equivalent across the battery, same thing. Now dt dt will get cancelled, and then when you integrate, you have at any given instant of time L1 I1 equals L2 I2 equals Li, where L is L1 L2 by L1 plus L2. So then an I is known as a function of time, E by R into that, right? So then I1 would be Li by L1, I2 would be Li by L2, where L is the equivalent and I is a function of time. So I1 and I2 are known as functions of time from these considerations. Now look, if there is a conductor PQ moving with a velocity V0, and placed from an infinite long current carrying conductor at a distance A, and this length of PQ is A. Realize that different points between P and Q are exposed to different magnetic fields. Why? Because I will produce different magnetic fields at different points along PQ. And then each of the elements of PQ would make a motional EMF contribution, but a different contribution because they are exposed to different magnetic fields, right? So if I had to look at an element, a small element dx at a distance x from this current carrying wire, then the magnetic field to which this is exposed is mu naught I by 2 pi x. That's a magnetic field to which it's exposed, and that magnetic field is into the plane of the board, right? Now if this has an upward velocity and B is into the plane of the board, then V cross B is leftwards. So this is a small current carrying conductor of length L. Instead of L you have dx, carrying a current I, exposed to a magnetic field mu naught I by 2 pi x. So it acts as a source of EMF to PQ. What source of EMF? B, right? This is B into V into L. BV, L is the EMF contribution made by this, right? And the polarity of EMF, d epsa, is like this. This is the d epsa that it contributes. This element contributes d epsa leftwards, right? All elements starting from x equal to a to x equal to 2a will make a contribution of this kind with the same semblance of polarity, right? So the net EMF produced between P and Q by all these elements dx starting from x equal to a to x equal to 2a would be sum of all of this, algebraic sum of all of this. X runs from a to 2a, that's the net motional EMF across PQ, with P being the positive terminal, Q being the negative terminal, based on V cross B, which is like mu naught I by mu naught I V naught by 2 pi log 2. That's the epsa across PQ. Clear? Now once you understand this, can I wipe this off? Problem 3. There is a frame thank God. This length you can assume is BQ, you can assume is small l, is this length BQ. So now let me explain the problem to you first. So we have a wire frame which is like a ABCD is a wire frame open at AB, and there is a slider PQ. there is a slider PQ which moves up along the wireframe and it has a velocity 2v, right? The wireframe itself has an upward velocity v. The wireframe ABCD has an upward velocity v, whereas PQ has a velocity 2v upwards, right? Now, PQ and CD act as sources of EMF, right? The equivalent circuit PQCD is then going to be, this is EPSA PQ, where in PQ instead of V0 you have 2V. In PQ instead of V0 you have 2V, and there is a EPSA DC. This is the equivalent circuit PQCD, right? Where EPSA PQ is mu naught I 2V by 2 pi log 2. What's EPSA CD? EPSA DC? EPSA DC instead of V0 you have V. That means EPSA PQ is larger than EPSA DC. That means you have a net driving EMF this way, driving a current I in the circuit, and the EPSA net for the circuit is going to be EPSA PQ minus EPSA DC. EPSA PQ minus EPSA DC. That's a net EPSA available counterclockwise in this loop, right? And EPSA PQ is like put V0 equal to 2V. EPSA DC is like put V0 equal to V. And if you subtract, everything else remains the same, mu naught I by 2 pi log 2, 2V minus V. That means V. That means the difference of these two is mu naught I by 2 pi V log 2. That's a EPSA net. So now this is a LR circuit. This is a LR circuit in which the current I driven would be at the behest of this EPSA net, and therefore I would be EPSA net by R into 1 minus e to power minus t into R by L. That will be the current time characteristic in this loop, right? So the current time characteristics for this loop I mean, if you want to call this I, let's say you call this I1, call this I1, I mean just to distinguish between this current and this current, right? Call this I1, this current through this conductor. So then this current I would be mu naught I1 by 2 pi V log 2 EPSA by R into 1 minus e to power minus t into R by L. That's the current time characteristic in this loop, right? We need to find the current when this PQ overshoots AB, falls off AB. One thing, the velocity of PQ is 2V. The velocity of this AB, imagine this AB to be a straight wire, is V. That means the relative velocity of PQ with respect to AB is V upwards, right? So the time it takes for PQ to overshoot AB will be L divided by V. L divided by the relative velocity would be the time that PQ overshoots AB, right? So then all that we need is current at time t equal to L by V. So put t equal to small l by V, you will find the current at an instant when PQ flows out of the frame. Clear? Have I discussed LC circuits in the class? Capacitance, and let me quickly then tell you the LC circuit scenario. I have discussed RC, of course, I mean LR circuit. I have not discussed LC circuit, right? LC circuit. So let me quickly discuss LC circuit with you. But can I wipe this off, and is this understood by all? So we now have a pre-charged capacitor, let's say with charge Q0, a capacitor C, charge Q0 minus Q0, right? And we align it electrically with an inductor L. This is at time t equal to 0. Now, through the inductor L, therefore, this charge Q would want to push itself through the inductor, and therefore there would be a proposal to drive a current in the circuit, right? So then this charge Q would vary with time, right? Let's say at some intermediate instant of time, the charge here is Q, the charge here is minus Q, and the current I is driven, gets circulated in the loop in this manner, positive to negative. At all instants, I could jolly well apply KVL to the loop. So now from here to here, what's the drop? Minus Q by C is the drop. Minus Q by C is the drop. Now, from here to, as I passes through this, the drop here will be L di dt. And this must add up to 0. Or we have di dt equals Q by LC. Di dt is Q by LC. Hey, realize that if this is the chosen direction, right, Q is decreasing with time, Q is decreasing with time, therefore dq dt is negative, dq dt is negative, and I mentioned to you I would be mod dq dt, I would be mod dq dt, and if dq dt is negative, mod dq dt would be minus dq dt, mod dq dt would be minus dq dt, because Q is decreasing with time, dq dt is negative, so minus dq dt. So di dt would be minus d2q dt2, minus d2q dt2, that would be di dt. Di dt you can write as minus of d2q dt2, and let me just place the minus here. Right? Which I could write as d2q dt2 as some minus omega squared into q, minus omega squared into q. Where what's omega? Omega is 1 by root LC. Way back when we were in harmony, SHM, we looked at the solution to this equation. D2x dt2 is minus omega squared x. I mean, does the equation know whether x is charge, or it's displacement, or it's the fan, or it's the light, or it's the TV, it's London, or it's Paris? The equation doesn't know all that, right? It's only you who knows that. So which means the solution to this equation, whether it's x, or it's q, or it's London, or it's Paris, it's going to be the same, the form of the solution, yes or no, right? The solution to this, one of the forms of the solution to this was x equal to a cos omega t. One of the solutions to this was x equal to a cos omega t. That was the solution of the harmonic oscillator. So then the form of the solution to this must also be similar. Given that at time t equal to 0, q was q naught. Given at time t equal to 0, small q was q naught, right? Leads to the solution to this similar to the solution of the oscillator as q equal to q naught cos omega t, commensurate with the fact that at time t equal to 0, q was q naught. The phase constant phi was determined out of those considerations. I mean, you could have taken q equal to q naught plus q naught omega t plus phi. Phi would have turned out to be 0 in the event we had a boundary condition t equal to 0, q equal to q naught would have led phi to become 0, and therefore q equal to q naught cos omega t is the explicit solution to this equation given an initial charge capital Q naught, capital Q naught, capital Q naught, right? So then in this case x undergoes simple harmonic oscillation. In this case the charge oscillates harmonically. The charge oscillates harmonically on the plates of this capacitor. This oscillates harmonically. Q versus time has a sinusoidal variation. Cosinusoidal is the same as sinusoidal, right? And what really transpires is, so there are instances when Q becomes Q naught, right? And this, we started with a total energy in the system Q naught squared by 2C, right? We started with a total energy Q naught squared by 2C, and that remains the energy at all times. That remains the energy at all times. What really happens is, when this Q decreases, from Q naught, then there is more current through the inductor, making the rest of the energy available as half Li squared in the inductor. That means this Q naught squared by 2C is partially in intermediate instance available as Q squared by 2C in the electric field of the capacitor, and if I is the instantaneous current, then half Li squared is the energy available in the magnetic field of the inductor. That's the energy implication of the circuit. It's a conservative, there is no resistance, there is no deprivation or bleeding of energy here, right? So then the total energy remains preserved commensurate with this. This will always hold good for the circuit. Sometimes when Q is large, I decreases and so on and so forth. That's the trade-off. Q versus I is the trade-off. A higher I would mean a smaller Q and therefore less energy in the electric field between the plates of the capacitor, etc. Clear? In fact, we could have started the problem by solving the Q versus time from these considerations. Like in SHM, we don't have to start with the force equation, we can start with the energy equation, differentiate and get the corresponding x versus time. In this case also, if I differentiate this with respect to time, left hand side would be 0. dq dt would be minus I, this will be 2I di dt, I would end up getting this equation. If I differentiate this with respect to time and put dq dt equal to minus I, I'll get this equation, the basic equation. And this was one of the practices in simple harmonic oscillation also. We wrote the total energy of the system at an intermediate and we differentiated that with respect to time and computed the omega and other things for the oscillator, right? We could have done. So omega is 1 by root LC. So then this charge shows a periodicity which is 2 pi by omega. The charge on this shows periodicity which is 2 pi by omega, where omega is 1 by root LC. It's called the angular frequency of the circuit. It's called the angular frequency of the LC circuit. Angular frequency of the LC circuit. Got me? Hey, this thought just dawned upon me right now, and I was wondering, Wednesday is Diwali, and I want to have a class that day. It can't be in the evening hours. It's originally scheduled for class 11, but what I feel is if I hold a class for class 11 on Wednesday, then it will suffer from bleak attendance and irresponsible behavior. They're not hard pressed for performance, taking it easy. They're still in a state of trance, and they're still honeymooning in a certain sense. But for you, the honeymoon was over long ago. I was inviting the prospect of having your class on Wednesday, dawn to dusk, and their class tomorrow. So what that would imply is they will show up, because they're not hard pressed to burst crackers tomorrow to that degree, and on Wednesday you'll be pushed to come, because your A's are on fire already. So might as well do this swapping if it's okay with you. No, sir. I knew that would be the resistance. Yet I know, despite the same resistance I would face from them, the only difference is I'll goddamn make sure that there is greater percentage of you arriving here Wednesday morning. And it's morning. Diwali is in the evening. Yes, it's the morning. I'm not saying evening. Yeah, morning. Those fellows would be averse to coming even in the morning. That's the thing. I mean, their Diwali had started like 1 week back. So what about meeting you in the morning on Diwali? We could be meeting as early as, let's say, 9 o'clock, like we do, and then we'll do as much as we could, and meeting them tomorrow. This swap. 10 o'clock? I think 9 o'clock would be good. I think 9 o'clock should be